Okay, cool. Then thanks so much. It is our great pleasure to welcome Sarah Bechtle for her talk on lifelong learning in the real world. Sarah is with the Max Planck Institute for Intelligent Systems in Tübingen and currently lives in Berlin, which is a wonderful city where I also only briefly lived. Sarah also has obtained her master's degree in Berlin from the Bernstein Center on Computational Neuroscience and an undergraduate degree in computer science from the University of Munich, the Technical University of Munich, right?
No, the other one.
Oh, the University.
Yeah.
Okay, from the LMU in Munich. And you closely collaborated with NYU, and you have also visited USC, so you have had quite some, seen quite some different places, and now we are very excited to hear about your work. Take it away. Thanks, and thanks so much for joining.
Yes, thank you a lot for inviting me. I'm really happy to present this work here, which is basically the work that I've done during my PhD, and which is centered like around this more like bigger question of how can you do lifelong learning in the real world if you are a robot. So what do we mean by this? So basically, we live in and learn from our world. And now if you want a robot to also to be able to learn in this world and to learn from this world, I think the robot needs to kind of go out and collect some data that is useful for whatever the robot is trying to learn, because then it can use this data to learn from it and update whatever it already knew from the world. And then this should be kind of repeated throughout the lifetime. So to also kind of be able to build upon what was already learned previously, to then continue and learn on top of that. And so why is this relevant? So I think that, for example, for we humans, we're really good at generalizing whatever we have learned. So when we learned how to peel a mandarin, for example, with our hands, we easily can learn how to peel a potato with a knife or with a peeler. And once we learned that, we can basically almost immediately transfer this to peeling a sweet potato with a knife, which is like a much bigger vegetable. And we might not be able to, do it perfectly the first time we do it. So we maybe cut away like more of the fruit and not just like a thin layer of the skin, but we still know almost immediately how to approach this problem. And my hypothesis is that we are able to do this because we learned kind of a representation of this task that then we can transfer to new tasks. And so if we want basically a robot also to be able to, after it learned how to peel a mandarin and cut a potato, how to peel and cut an apple, for example, I think we really have to understand how to learn representations that generalize quickly to new tasks. And I think this is something that is one aspect of how to do lifelong learning from the data that you experience in the world, like from this dynamic data that you collect in the world, which is different like from these static data sets that we can use for a lot of other machine learning applications. So what I have worked on during my PhD is like two aspects. So one aspect is how can you learn a representation of the world? So this goes a lot into the direction of model-based learning. And then another aspect is how can you actually learn a representation of the learning problem itself? So this goes more into the direction of learning to learn or meta-learning, kind of to try to learn an abstraction of how to approach a learning problem. And I'm also going to structure this talk like with these two sections, basically. So in the first part, basically also again looking at humans, the human brain actually builds cognitive maps of the world. And these cognitive maps that we use, we can actually reuse them later on for faster learning of new skills, for example. And we also are selective of how we build these cognitive maps. We don't always take all the information into consideration, but we can also discard the things that are irrelevant for this one cognitive map or for this basically cognitive map that we're trying to build right now. And so from my perspective, like if we want to transfer this into a robotic setting, we have this robot, and this robot is kind of placed in this action perception learning loop. So where the robot acts in the environment, collects data, and learns from this environment. And specifically, I looked at how to do model-based learning in this loop. And so with model-based learning, it has like a lot of, I mean, it comes with a lot of promises, for example, that it's more sample efficient, that it transfers better. So again, this idea of basically transferability, but it also has like some really significant problems. And one of these problems is that, for example, if you have a bad model, you're going, since you use this model to plan or to learn a policy, you're going to learn a policy that might be not very good in reality. So it's a suboptimal policy that then when you use on the robot to collect data in the environment, you're going to collect some data that might be completely irrelevant for what you're trying to learn. And it might have basically very little information for the task you're trying to achieve. And this can actually even lead to somehow a worse model. And this whole learning problem stabilizes in this suboptimal solution that it's very hard actually to get out of. And this has also like been discussed already in previous literature, that this is like one of the kind of the bigger problems of model-based learning. And so the question is the question that I asked myself in the PhD is, how can we learn better models? And so I've looked at this like from kind of 3 different perspectives that I'm going to present now. And so 2 perspectives are really, I mean, all of these perspectives are actually inherently concerned with how can you get data that helps you with learning. And so in the first project, I'm going to talk about how can you do exploration in this model-based learning setting. In the second work, we really try to see out how can we actually optimize a policy or learn a policy by considering already during learning the quality of our model that we're trying to learn, because we want to because the policy can enable us to learn a better policy, a better model, basically, because it's the component that collects the data. And then a different way of like trying to maybe learn a model that generalizes better to new tasks is how can you use structure while learning? So there is structured information, especially in the robotic domain, for example, kinematic models or dynamic models that we could actually leverage during learning. And all of these things, I think, are maybe approaches to help learning these better models. So in this first work, we looked at how can you explore, how can you collect better data through exploration. And so most of the exploration work in reinforcement learning actually happens in the acting phase. So by, for example, an epsilon greedy strategy, or like some noise added to the output of a policy in order to change a little bit the data distribution that you see, and therefore also collect different data that might be relevant for the task. Sometimes also just by accident, you might encounter this better data. But we really wanted to look at how can you include basically this exploration objective already during planning, so during policy optimization. And this goes more into the direction of kind of intrinsic motivation literature. So how can you optimize a policy already with the objective of exploring? And so most of the work that looks at intrinsic motivation actually looks at model-free reinforcement learning algorithms. But we here in this case wanted to really look at the model-based reinforcement learning algorithm and how can you optimize a policy that explores. So for this, we presented this model-based reinforcement learning framework where you learn a probabilistic model of the dynamics of the robot, and then you optimize what we call a Curious-ILOR policy that uses this probabilistic dynamics model and specifically kind of exploits the predictive uncertainty of this model in order to kind of optimize a policy that seeks out areas of the dynamics model that have higher uncertainty, to go in there and to learn from these areas with higher uncertainty. And so this Curious-ILOR policy basically leverages some results from the optimal control literature, where it has been shown that you can basically extend ILOR to a risk-sensitive stochastic optimal control problem by exponentiating the cost function. And so the cost function, you still make this quadratic assumption of your cost function, you still make the linear assumption of your dynamics, but you can basically show how by exponentiating this cost function, you can find the Riccati recursions to compute the optimal feedback policy that specifically includes also the variance of the cost. So the second moment basically of the cost. And this, in the case of our work here, 1 second, it doesn't move the slide. Oh, okay. So in the case of the work that we presented here, we have this probabilistic dynamics model. And this probabilistic dynamics model predicts kind of a distribution over the next state that also has a predictive uncertainty, the sigma here. And since we use this dynamics model to optimize the policy, the variance from the cost really comes from the predictive uncertainty of our learned dynamics model. And so you can formulate this extended form of the Bellman equation that still contains here the part that is that basically is concerned with the cost. Like this would be a normal Bellman equation, but it also includes the predictive uncertainty. And how this predictive uncertainty is included in this problem really depends on this small parameter here. So this sigma parameter here, the small sigma parameter here, you can really choose, and you can make it a risk sensitive problem, but also a risk seeking problem. Namely, when you make this sigma parameter negative, this whole cost, this whole basically equation here becomes smaller, so it has lower cost when the predictive uncertainty is higher. And therefore, we are going, as an effect, basically going to explore into parts of the dynamics model that have high uncertainty while staying close to our desired basically goal. So while we're still looking at our cost.
And
so
Sarah,
usually,
I ask a question.
Yes. Yeah.
So your dynamics model is the probabilistic dynamics model. Is it a Gaussian process, or do you learn it like a Gaussian process? Did I understand correctly?
Yes. So we learned it with a Gaussian process, but also with ensemble of probabilistic neural networks.
Oh, okay.
Yeah. So we tried both, and I think in the paper we have also both results. But at the beginning, we started basically with the Gaussian process regression because it has this kind of nicer, like predictive uncertainty properties.
But so the problem of if you use Gaussian processes, basically that your state space has to be relatively small, so you cannot do something like, I don't know, like in Dreamer, these latent world models will become hard because they're already the latent space, the state spaces are almost too big for Gaussian processes.
No,
what
exactly.
are your thoughts about like the size of the state space in that context? Yeah,
so we did the experiments on a 7 degree of freedom manipulator. So that already I would say, I mean, it worked, but I think, right, you cannot increase the dimensionality much more. So we used also sparse Gaussian processes. So that helps a little bit, but this is actually then also why we decided to try the ensemble probabilistic neural networks, because of this reason. Because if you want to transfer it to a different problem where you have a higher dimensional state space, then it becomes not like you can't really use the Gaussian process anymore. So yeah, this is definitely a problem, and I think it's still like a little bit of a challenge or something to basically work out how to get some predictive like some predictive distribution. How can you basically capture the uncertainty when you have high dimensional state spaces, like, because with the neural networks is not 100% clear how the predictive uncertainty behaves, especially when they're trying to extrapolate somewhere. So I think that's still a question, but so it's definitely something to keep in mind.
Okay, can I ask another question?
Sure.
So as far as I can understand, there are two ways to think about reducing uncertainty in the dynamics in general. One of them is to sort of try to take actions that are going to lead the robot to collect data where, in places where the dynamics are uncertain. And the other one is sort of to figure out, places of high uncertainty, but also that are useful to the planning problem, in the sense that the cost function is going to be uncertain as well. And you're trying to figure out where the cost function is going to be, where you need to take actions in order to trade off this risk of collecting useful data versus optimizing your task performance. So in the second option, things are a bit more coupled. And I just wanted to confirm that what you're showing us here is the second option, or is it the first option?
No, that is the first option. So basically trying to explore into the part of the state space that have high uncertainty in order to collect data there. So I think that the second option that you're talking about is a bit more related to Bayesian optimization, right? Like where you kind of try to sample where you have high uncertainty in your cost.
Yeah.
Yeah, and so in this case here, basically we're trying to sample where you have higher uncertainty in your dynamics model. But I mean, you're right, because it's since the way how we in the end we operate. So in the end, actually, it's related, because we are also since we compute the cost through our dynamics model, when we have high uncertainty in our dynamics model, we will also have a high uncertainty in the cost, but it's kind of coupled to the state.
Right. I guess what I'm trying to get at is that there are a few works and traditional literature from adaptive control theory, which shows that you actually do not have to learn the perfect dynamics model. You can in fact converge to the wrong parameters of the dynamics, as long as your task performance does better, or is guaranteed to do better. In some sense. So I guess what I'm trying to understand is, does this formulation basically force the perfect dynamics to be learned, or does it learn the part of the dynamics that is necessary for the task?
Yeah, it learns the part of the dynamics that is necessary for the task. Like ideally, it would learn, also the parts of the dynamics that, or ideally it would learn like a perfect dynamics model. But what it's doing in practice is it's learning the basically a good dynamics model for the task that it's trying to solve. And I mean, I think in this case here, because we're doing like a gradient-based optimization, the thing is, we only see the real data when we do the rollout on the robot to collect more data to update the model. So we don't really evaluate, we don't really consider in the optimization problem the actual achieved cost, because we don't see it during the IQR optimization, since we only see whatever our dynamics model is predicting. But in the end, what we're going to learn is a dynamics model that works well for that task, and for maybe goals that are around that current goal, let's say. But we will not really learn. I mean, I don't think we really learn a perfect dynamics model everywhere in the state space.
Got it. Thank you.
Sure. Yes, so in these plots here, basically we show the kind of the performance of this Curious-ILOR algorithm, and in the plot on the left, you can see over the real system iteration, so how often we actually run the policy on the robot to collect data, how the kind of the error to the desired end effector position develops. So. And here in orange, there is our Curious-ILOR policy. And we can really see that this one, by kind of considering the predictive uncertainty in the model, it really is able to converge to a good solution where it reaches actually the end effector, the desired end effector position also on the robot much better than in the other cases. So for example, the blue line specifically is if we do not consider any variance in the cost, basically, but we just do normal IQR optimization. And here in the plot on the right, you can see how the forward model prediction error decreases. So also really showing that the model is predicting much more accurately with the data that was collected with our Curious-ILOR algorithm. And so really having a model that for this task has much more accurate predictions compared to the other ones. And now basically it could be right, and this is like kind of this interconnected problem here, that the task performance might be better because the forward model prediction error is lower, but it could also be that we get learn a better model because we are actually having a better policy that collects better data. And this is like these two kind of how this is connected is basically, I think, also a little bit of the challenge here, because you can only basically to update your model, you can only use the data that you saw given your policy. And so now, and then we did also some generalization experiments where basically we wanted to reach goals that we didn't see during training. Yeah, so these experiments before were like on a reaching task on the Sawyer arm. And now these are new goals. And here the Curious robot, which is the one on the left, is actually able to reach these new goals much more accurately compared to the normal robot that doesn't use any exploration in the learning problem, that just does your ILQR on the dynamics model that was learned. And so the reason why this normal robot isn't doing anything really useful is because, so I mean, the optimization is still ILQR, right? So it's actually trying to minimize this cost that it's seeing giving the model. So it means the model is predicting somehow that it's reaching the goal position, because otherwise the optimization wouldn't converge, but it did converge always. But it's just not true in reality. So it's predicting it's reaching the desired goal position, but it's actually not reaching the desired goal position. And this problem, this discrepancy is called model bias, where the model is kind of biased, or often like more optimistic, predicting that it's, you know, achieving whatever it should achieve, but it's actually not happening. And we wanted to analyze this problem a bit further in this other work here, where we are again in this model-based learning loop. But this time we learn policy as a neural network as well. Like as it's again, this time it's a neural network policy that we learn, and it's not an optimized policy. And we also learn a dynamics model, also as a neural network. So these are completely, in these experiments here, completely learned kind of parameterized by neural networks. And we connect these two things. So basically the inverse model of the controller takes as an input the current state and either the desired next state or a desired goal state, and outputs an action. And then this action is taken as an input to the forward model together with the current state as well, that then predicts a next state. So it's predicting basically the next state given the current controller. And now this next state here actually is a function of the parameters of the forward model, of course, but also of the inverse model, since we inputted this, the action to the forward model. And this now allows us to compute a cost function in the state space that we can use to optimize our policy or our controller. So since, you know, the next state is also a function of the parameters of the policy, we can actually compute a cost function to optimize the policy in state space. And now the most like straightforward like idea that you can have is that you say, okay, I want my predicted next state given my controller to be similar or equal to my desired next state or to the desired goal state. And this would be like kind of the most like intuitive way of going about this problem. So this is my loss function. I want that my predicted next state given my controller is equal to my desired next state. But if you analyze this loss function here, you can see that it basically reaches its equilibrium or converges whenever the predicted next state is equal to the desired next state as per definition. But it doesn't really tell us anything about if we really achieved this new state on the robot. So we have to fully trust, blindly trust basically the forward model. And so we propose this other loss function where instead of only, so when we are learning the policy, instead of only considering this predictive task loss, this predictive task performance, we also consider the performance of the forward model. So how well did our forward model actually predict the next state? So essentially kind of trading off the predictive task performance with with basically the forward model quality. And if we do an analysis on the gradient of this loss here, we can see that this actually reaches its equilibrium in this model-based reinforcement learning loop when the desired next state is equal, when the predicted next state given the current controller is equal to the desired next state, but also to the actual next state. So really achieving the desired position also in reality. And maybe to illustrate this a bit further, I did like a really kind of simple example where we have a policy that is parameterized with 2 parameters only. And we create artificial model bias everywhere in the state space. So the forward model is always predicting the desired next state in a trajectory. And when we look at the gradient fields here in our joint loss, we can see that no matter where we are in the parameter space of the policy, so beta 1, beta 2 here, we always find a gradient that points towards the optimal values of beta 1 and beta 2, which is this blue line here. So no matter, like, even if we have this model bias, no matter where we end up in, no matter where we are, we will always be able to recover the optimal parameters of beta 1 and beta 2. And this is not the case for our task loss here, because as it has 0 gradients everywhere in this parameter space, and therefore it's not continuing to optimize the policy, even though obviously, you know, the parameters are not the optimal parameters of the policy, and it will never really reach these optimal values of beta 1 and beta 2. So this really means that this loss function here is really trying to tackle this model bias problem. So how can you have a model that predicts the right thing? And we could also see that really on our experiments, like on this quadruped, so this quadruped should follow a walking trajectory, that also in these experiments, we are actually able to achieve much better performance than compared to our other, to the baselines, basically. I mean, I don't show the baselines here, but you can see that in iteration 0, it's kind of not really learning anything useful at this point, and then towards iteration 8 it already gets a bit better, and then towards iteration 20 it actually really learned to follow this walking trajectory here. And if we look at this plot here, we can also see that compared to the baselines, this joint loss, which is the blue curve here, really outperforms all the other ones. So really is the only one that is actually really able to make this quadruped walk, and the other ones, they don't, the policy will not learn to walk. And the reason why this is the case can be seen here in this plot here, where in the top you can see the forward model prediction error, which is very, very low for our joint loss, but it's actually quite high for this predictive task loss. So the forward model that was learned with the policy that was learned with the task loss has much higher prediction error. But if you look at the predicted task error, it actually has lower predicted task error compared to our joint loss. However, like, this is not true in reality. There is a huge gap between like this and basically this line here. And this gap is really the model bias. So the model is thinking it's doing the right thing, but it's really not doing the right thing. And this is why it's also not able to really ever learn this to follow this walking trajectory. So now the last project in this part of the talk is about how can you actually include structure into the learning problem. And for this, we wanted to see at specifically how can you fuse visual information with more structured proprioceptive information when you want to detect key points on the object and that is in a manipulator's hand. So we took this this key point predictor here and extended it with a kind of a kinematic component, where we take the joint state of the robot and we project the end effector position into image space and create a kinematic feature map. So this kinematic feature map then we combine with the visual feature map that is coming from an encoding step on the RGB image. We combine this in the latent space, and then we decode this combined feature map to recover these key points on the object in the manipulator's hand. And we can really see that with our approach here, we can, which is the video here on the left, we can really recover key points that are placed much more accurately on the bottle compared to the baseline that doesn't use this kinematic information and has like key points a bit all over the place. And especially also you can see here that the key points are shifting. And this is really not such a good situation if you want to learn from this key point data, for example, if you want to learn a visual dynamics model. And so learning a visual dynamics model, for example, is important if you are trying to do some downstream task with this information. So for example, if you want to place the bottle on a table or on a shelf. So you could use this data now here that is coming basically from your camera, where you detect the key points on the object in the manipulator's hand, and you could learn a visual dynamics model as a neural network, where you take where you have the current state and the action, you predict the next state in the visual space. So how the key points basically shifted. But we actually decided to take also a more structured approach here. And so instead of learning kind of this visual dynamics model as a neural network, we learn an extended kinematic chain of the robot, where we add like some virtual joints that kind of, some virtual joints that do not really exist, but on the bottle that it should be in the manipulator's hand. And then we regress these joint parameters here, the translation parameters of this joint from the visual data. And we can really see that by doing that, we were able to perform very well these placing tasks because there is a certain consistency to the predictions of this dynamics model, which you can also see in this plot here. So the long horizon prediction error of our kind of model, which is this extended kinematic chain here, is always 0, because is always very close to 0, because it doesn't change, right? The kinematic chain is fixed. It was learned, but it's fixed. So this has other problems, because once you place the object and you retract, you have to adjust to that. So we didn't do that, but still during the manipulation task, it helps a lot to have more of the structure. But interestingly, you can see here in this the other baseline that didn't do so badly in the long horizon predictions is this brown line here. And this is a baseline that was learned from the data collected with our Keypoint detector. So also already, and then trained as a neural network, a dynamics model. And so already having like this better data, because we use structure during a kind of this Keypoint detection. So we kind of use structure while doing, trying to kind of use this visual information. Already this helped as well to increase the model's quality. So in this first talk, part of the talk, I talked about this, basically how you can collect data mostly that allows to learn a good representation of the environment, or in this case, mostly of the kind of the contact dynamics, the robot dynamics, and the kind of object dynamics in a manipulation setting. And specifically like looked at how can you basically do exploration, or like kind of alleviate this model bias problem, and also how can you use structure to get this better data. And now in the second part of the talk, I'm going to talk a bit more quickly about a different kind of representation that you can learn, which is like a representation of the learning problem itself. So how can basically the robot learn to learn? And we definitely can learn how to learn. And there's actually, we believe that this is what allows us to generalize, far beyond whatever we have seen, because we can easily know what we need to do in order to learn what we want to learn. And I think in the robotics setting, mostly this is called meta-learning. And in general, let's say in learning, we are trying to learn this function f, and we're basically trying to find the optimal parameters of this function f. And we do this by using a loss function, and then we have some gradient transformation in order to make the update on the parameter and get the better parameters. And so now in the majority of deep learning, actually, we try to learn this f function directly from data. So, we have a data set and we try to basically fit these parameters such that they best explain the data that we see. And then in meta learning, there is some work that is looking at how can you learn these gradient transformations. So how can you actually learn the transformation, the best way of making this parameter update. Then there is other work, which is specifically MAML. I think the most famous one is how can you basically learn a representation of the parameters of your function f, so that you can learn somehow a good initialization for these parameters that then can generalize quickly to new situations. But in the work that we presented, we looked at how can we learn a loss function. So how can we basically learn the learning objective, which is the loss function? And we think that this has some benefits because loss functions are more general, actually. Like we use, for example, the mean squared error loss for a lot of different things. And they are also quite architecture independent. So you're not then bound to one specific form of architecture with a specific type of parameterization, but you are more flexible in that sense as well. And so this framework we presented is made out of two parts. So there is an outer loop where we learn this loss function network M that is parameterized. So in this case, it's like it can be parameterized, for example, by a neural network. And this loss function network, this loss network then outputs a loss function L. And this loss function L then is used in the inner step where we are trying to learn this function f as the objective. So we basically make an update on the parameters of f. So we compute theta nu by taking a gradient step of this learned loss with respect to the parameters of f. And we can do this because the output of f was an input to m as well. So there is a connection. And specifically, like if you so this is how these two loops are connected with each other. So this is how you update the function f. And then to update the outer loop, you look at how well did your function f with the new parameters now do in achieving your goal G. So you have some goal information, for example, like a goal position in a reinforcement learning setting. And we compute a task loss here. And this task loss now is actually defined. So you can define this task loss. You can, for example, say you want to reach this goal location of your end effector. And then since f was updated given the learned loss, now we can also update the parameters of the loss network phi with a gradient step. So we can, this whole loop here is basically it's fully differentiable. And then during meta test time, actually, or let's say after we learned the loss function L, we only need this loss function L. We don't need to train M anymore. We can just use the learned L to update F. So what is interesting here is actually that in this meta training phase, so when you're still training your loss function M, you have to define this task loss. And this task loss you can also define by, for example, adding some extra information, some information that you say, okay, you have available during training, but it might be expensive and you cannot always have, don't always have access to it. So for example, in this very simple example here, where we're trying to learn the frequency parameter of the sine curve here, we say, okay, during meta train time, we have access to the optimal values of theta. So only for a very small amount of data, we have access to the optimal parameters of theta, but this one we can use during meta train time. And we can see, for example, here that if we, even if this is a very simple problem, but if we just use the mean squared error loss, we have a very non-convex issue here problem to learn this frequency parameter of the sine function. There's a lot of local minima the optimization can get stuck in, and it would be really hard actually to optimize this with gradient descent. But if we use our kind of extra information during meta train time for like only a certain amount of data, we can nicely shape this loss landscape to become a convex loss, because this problem here actually is convex. And we can have this convex loss function that then we can use also at meta test time for different sets of parameters or for different sets of data, and recover very easily the optimal value of the frequency parameter, because the loss is convex and therefore the optimization will converge very quickly. And this is just like really happening in this inside loop, but from the outside, everything looks the same. So the inputs to the networks respectively are always the same. You're just changing this, whatever you see basically inside of the loop, and this learned loss can somehow inherently capture that. And so we did a lot of different experiments with this framework here, and specifically we did also reinforcement learning experiments because they're like more interesting, let's say, for the robotics domain. And I'm going to present here now some model-based reinforcement learning experiments where you have a dynamics model P, and your task loss, basically what you'll use during meta train time is to maximize the expected value of your reward given the current policy. So you also learn the policy in the loop. This is basically then your F is your policy in that case. And you're trying to maximize this reward that you get through this dynamics model. And so in this sense here, you could look at the dynamics model as being some form of extra information during meta train time that you get in order to be able to compute the gradients of your reward function. So this, for example, you could also use an analytic model. This is what I'm trying to do right now, to use an analytic differentiable model in order to learn this loss function that then hopefully captures these gradients, and you can use it later on in a model-free way. And so here in this experiment here, we use these two targets during meta train time. And this also shows a bit how well it generalizes, how this loss function really is generalizing, because after training on these two targets, during test time, we could extrapolate basically learning the policy to do these 4 new targets that weren't seen during training. And specifically, what is interesting is that, so first of all, the optimization is very fast. So it depends a bit on how you train it, but you can do it in like one gradient step. And the other interesting thing is that this becomes a completely model-free update then. So you had the model during train time, but during test time, the model is not needed anymore, because the loss function captured these gradients through the model itself in the loss function itself, and then you can do model-free updates only given the learned loss. And so I'm currently thinking about like that it could be interesting, for example, to then use this as a good like initial guess of whatever you're trying to do in a new context, and then you could, for example, keep fine-tuning with a model-free reinforcement learning algorithm, or yeah, basically use it as a good initialization. So I think also that this is something important about learning to learn, that we don't need to think about this as being, you know, learning something that will immediately generalize 100% perfectly to a new scenario, because I also don't think we are able to do this. But I think we can basically, it should help us to not having to start completely from scratch whenever we are encountered with a new situation. And another form of expert knowledge that we used during meta training is visual demonstrations. So we humans are very good at learning from visual demonstrations. We see something from when we are very little and we try to copy it. Like even if we see, like, for example, this kid here in a TV, we basically we can make kind of sense of what we see and try to copy it into our own actions. And so we tried basically to do the same thing for displacing task, where we had a human demonstration in the visual domain. So the demonstration was captured in this Keypoint space. And then we learned a loss function that then would allow the robot to place this bottle as well. And so this goes much more into the direction of kind of inverse reinforcement learning using this bi-level optimization framework, where basically the policy learning and the loss learning are connected, and the loss is being learned by trying to improve the learning progress of the policy. And yeah, so in this case here, basically these human demonstrations were used as an extra information, because we would also assume we only have a limited amount of human demonstrations and not that many. So it would be nice to somehow capture it into a reward function, for example. So in the second part of the talk, I presented this learning to learn framework that learns a loss, which for me, a loss is basically kind of a representation of the task and of the learning problem itself. So you're trying to kind of learn the learning objective that you need in order to learn something. And everything is basically happening also in this case in this action perception loop. So you always try to run the policy in the robot, collect more data, see how well you improved, and then adjust your learned loss to increase this improvement in the policy. And also if you use expert demonstration, it still follows the same idea. So you're still trying to improve this policy. Yes, and then coming back to this question, like how can we actually learn these representations that generalize quickly? I think, well, this is like somehow, you know, this work that I just presented answers some aspects of it, but there is like much more. And I think so I'm especially interested actually in looking at how can you use this structured information or analytical information like the kinematic and dynamics model, especially during learning to learn. So how does it help, you know, to leverage this this embodiment of the robot that we have as an inductive prior in these learning to learn problems? And how does it help us? Like, does it help us because then we can basically learn faster, meta learn faster, or does it help us because it will actually allow to meta learn a loss function that generalizes then better to new tasks? And what I also think is really important is, and I did do it a little bit, but not that much, is to use much more multimodal sensory information to learn these representations of the environment, because I think the more sensory input you have, the more actually connections you can make between similarities of contexts that you are in. So if you look at only like two sensor modalities, for example, it can be very hard actually to discriminate in which setting you are in right now. And I think this becomes more important once we maybe move away from only looking at things that are like immediately part of the robot's body, but like trying to learn a representation that is, you know, maybe a bit more kind of more abstract, like more context, more representing a context instead of representing an internal state. And then I think, well, I mean, I think that other things that I'm interested in working is, for example, how can you combine these model-based and model-free reinforcement learning approaches? So there is also like a lot of evidence that actually this is happening in the human brain as well. And so this is also what I'm trying to do a little bit now with seeing, okay, how can you use the model maybe at the beginning, but then you can continue fine-tuning in a model-free way. But actually the other way around could also be interesting to say, okay, you have these kind of more reactive model-free policies, that allow you then to collect the data that you need in order to build the models that then you can use later on again. And in this setting here also, obviously, like, how do you discover basically goals that are relevant for you specifically? How do you discover goals where you get the data that you need in order to learn? And I think, for example, something that I find very interesting is to think about, like, how can we exploit these, causal structures that we have in our environment, because we are learning in the real world. So there is a lot of causality happening there. And how can we basically exploit that as well when we do reinforcement learning in terms of like internal learning signal that we can use for learning. And this also goes a bit into the direction of basically active learning. So yeah, thanks a lot for inviting me again and for listening to the talk. And I would like to thank all of my collaborators and the places where I was able to do the research, and would be happy to take any questions or discuss about some parts of the work.
Yeah, thanks so much for the super interesting talk. There are tons of applause, but unfortunately in Zoom it's hard to hear. Sarah, once again, thanks so much for taking your time today and for giving the great talk. It was super interesting.
Yes, thanks a lot again for having me. I really enjoyed it.
Yeah, it was wonderful to have you. We wish you all the best with your research, and we hope to meet in person at some point at one of the future conferences at least.
Yes, that would be nice. Have a good day then.
Yeah, thanks so much, everyone. See you.
Bye-bye.
See you. Thank you.